Hello friends, I am Dr. Sangeeta Patil, Assistant Professor in the Department of Electrical and Electronics Engineering, MIT School of Computing, MIT ADT University. Welcome you all for a course on Basics of Transformer. Let us start the lecture. See, the iron core of the transformer is subjected to the alternating flux. So the core losses, that is hysteresis loss and eddy current loss, both losses are always present in the transformer even though your core is laminated to reduce the eddy current loss and your core is made up of high grade silicon steel to minimize the hysteresis loss. Therefore, even under no load condition, what is no load condition? It means that your secondary is open circuited. So, even though under no load condition, your source must supply the enough power to the primary winding so that the core losses will become overcome. Okay, so therefore, in case of the transformers which are used in the actual practice on no load, that is with no current in the secondary winding, the primary winding always carries small amount of current which is denoted by I naught, It has two components. First component is I naught has two components. Your first component is I magnetizing and second component is IC. So what is I magnetizing? I magnetizing is nothing but a reactive or wattless magnetizing component. Wattless magnetizing component. And IC is nothing but an active. It is an active component. I magnetizing is a reactive component. IC is the active or power or core loss component which supplies mainly the core losses and the negligible copper loss in the primary winding, because primary winding has also some resistance. So this IC will take into account the losses. Which losses? Core loss and negligible copper loss in the primary winding. So your I naught is nothing but vector sum of I magnetizing. What is I magnetizing? The component of no load current which is required to set up the flux. That component is also called as a reactive or wattless magnetizing component. It is responsible for producing the magnetic flux and hence it is in phase with the flux. Okay, and second component is IC. What is IC? It is an active or power loss component or core loss component. It supplies mainly the core losses and negligible copper loss in the primary winding of the transformer. This component is in phase with the component minus E1 of the impressed voltage. Means this is in phase with the opposition with the E1. It is in phase opposition with the E1. Okay, so where is your E1? E1 is here. So whatever the diagram I have drawn here, I will again draw for you people in step by step. So let us draw the phasor diagram of your ideal transformer or practical transformer which includes the core losses. Okay, so students, what is your reference vector? Reference vector is nothing but the voltage. V1 which is applied across the primary winding, right? So V1 is applied across the primary winding, right? Then when this V1 is applied across the primary winding, I magnetizing is circulated, right? So this I magnetizing component of your no load current is responsible for setting up the flux, right? So the flux produced by this current is always in phase with the I magnetizing. So I will draw the flux in phase with the I magnetizing. Now when this flux link with the primary as well as secondary, it will produce the EMF of self-induction in the primary and mutual induction in the secondary. So this is your E1, that is self-induced EMF produced in the primary winding, and this is your E2, the mutual induced EMF when your flux gate links with the secondary winding, right? So as your secondary is open circuited, my E2 is equals to V2. It is open circuited, so E2 is equal to V2. Now this current is not only magnetizing in the circuit, but it consists of your no load current taken from the supply. It consists of two components, core loss component or power loss component IC, which is in opposition to that of your E1. Yes, so this component is in phase with the component minus E1. So this is your E1. So I will take minus of this component on the upper side. So this V1 is approximately equals to minus E1, and this component IC will overcome my core loss. Now I0 is nothing but vector sum of your IC and IM. So I will take the vector sum of both current I magnetizing and IC, so that I will get the no load current I0. I will get the no load current I0. So this is your I0. This is your I0. Okay. So this is your IC. So this is also IC, which is parallel to this, and as this is your magnetizing component of no load current, this is also IM, that is the magnetizing component, right? So the angle between voltage, applied voltage, and the no load current taken from the supply is nothing but phi 0, which is nothing but no load power factor of the transformer. No load power factor of the transformer. So from this figure we can write down these formulas. Okay, so here I have taken vector sum of IC and I am magnetizing, so that I will get the no load current I0. So from this triangle, as this is your phi 0, from this triangle I can write down I0 is equal to under root of IC square plus I magnetizing square, right? Or for simplicity, this I magnetizing you can write down as IM. Okay. Then what is the power factor on no load? Power factor on no load is nothing but cos of phi 0. So cos of phi 0, this is your phi 0 angle. So what is cos of phi 0? It is nothing but IC upon I0. IC upon I0. The core loss component IC being usually very small as compared to your magnetizing component IM, the no load power factor is very low. The no load power factor of the transformer is very low. Hence, we have drawn the phasor diagram of the transformer by considering the core losses, and that phasor diagram is drawn for no load. Now, let us see the effect of the resistance and leakage reactances of the winding. So, let us see the effect of resistance and leakage reactance of windings. We have seen the effect of the losses on the transformer. Now let us see the effect of the resistance and leakage reactance of the windings. In practical transformer, each winding of the transformer has two windings, P and S, that is primary and secondary, right? So each winding possesses certain amount of finite resistance, which apart from causing a power loss also produces the voltage drop in it on when current starts flowing. So if your primary is connected across the supply, current starts flowing I1 in the primary winding, right? So apart from causing the power loss in the primary winding, this current also produces the voltage drop in the winding when current starts flowing. Also, this electric current as an electric current, magnetic flux cannot be completely confined into the desired path, right? Therefore, all the magnetizing flux produced by the primary winding of the transformer does not link with the secondary winding, but some part of this flux also complete the magnetic circuit by passing through the air rather than around through the core. Means some of the flux so this is your flux of the primary which is linking with the secondary. Most of the flux completes its path through the magnetic core, but some of the flux will complete its path through the air rather than passing through the magnetic core, and such flux is called as primary leakage flux. Such flux is called as primary leakage flux. This leakage flux does not contribute to the transfer of energy from primary circuit to the secondary circuit, and therefore there is no use of this flux, right? So this serves no useful purpose since it fails to link with the secondary winding from the primary winding. Now, when secondary winding also produces the opposing flux due to the current flowing through the secondary winding, if it is connected across the load. Suppose here I will connect the load. Suppose here I will connect the load. Then what will happen? Current starts flowing in the winding, right? 1 minute. So current starts flowing through the secondary winding. That current is nothing but your I2, right? So secondary winding also produces the opposing flux due to the induced current flowing through it when it is connected across the load. Major portion of this secondary flux links with the primary through the magnetic core, right? But some of the flux also complete its path through the via air. However, some amount of this flux links only with the secondary winding through air as shown by the dotted lines, and this flux is called as secondary leakage flux. Secondary leakage flux. So these primary and secondary leakage fluxes produced in their respective winding, they will produce the self-induced EMF, which are proportional to the current and the frequency. They are therefore equivalent to an inductance placed in series with the each winding. Because as this flux is linking with this winding only, they will produce the EMF of the self-induction. So, and that EMF of the self-induction is proportional to current and the frequency. Therefore, the leakage flux of that respective winding is considered as a inductance equivalent to an inductance which is placed in series with that winding. The reactance of that inductance is called as the leakage reactance of the winding. Similar to resistance, both primary and secondary leakage reactances cause the voltage drop in the respective winding. So the combined effect of voltage drop in respective winding or the voltage drop due to resistance and leakage reactance of the winding of a transformer is ultimately changes its terminal voltage on no load from its no load value for a given applied voltage across the primary winding. So students, the combined voltage drop due to the R and X. R is nothing but resistance of that winding and X is nothing but the leakage reactance of this winding. So the combined effect of voltage drop due to the resistance and leakage reactance, of the windings of a transformer is ultimately to change the terminal voltage on load from its no load value. So your terminal voltage will get drops down. The leakage reactance is normally minimized by placing the windings on both the limbs of the core, half on each of the limb. That's why at the time of taking the construction, I have told you that instead of for the elementary transformer, I have shown the primary winding on this limb and secondary winding on this limb. But in actual practice, half of the primary winding is placed on this limb, half of the primary winding is placed on this limb. Same thing is true for your secondary winding. So how to limit the leakage reactance or how to minimize the leakage reactance? We have to place the windings on both the limbs of the core, half on each limb, and also by subdividing or interleaving the different section of the windings. So in this way, we have to take into account the effect of the losses as well as resistance and leakage reactance of the windings. Now, students, let us start for drawing the equivalent circuit of the transformer according to the concept that we have studied to take into account the effect of the losses and the effect of the resistance and leakage reactance of the winding. So the analysis of the transformer performance can be conveniently made by using its equivalent circuit. An equivalent circuit is nothing but the circuit whose behavior is similar to that of the transformer. So we are going to draw one circuit whose behavior is similar to the behavior of the actual transformer. And such an equivalent circuit we can develop by initially assume the transformer to be ideal one. Okay. So initially I will assume that my transformer is a ideal transformer. Then the different imperfections of the actual transformer I will allow for by means of additional circuits or impedances or inserting them between the supply terminals and the primary winding and between the secondary terminals and the load. Okay. So here let us draw the ideal transformer. So I have drawn this transformer symbol. Let this transformer is an ideal transformer. Let us denote here the M is the ideal transformer. So here M represents the ideal transformer. What is ideal transformer? Transformer with no losses and no magnetic leakage and having the iron core of infinite permeability requiring very small magnetizing current to set up the flux, right? Then now let us add the different imperfections of your actual transformer one by one. Now let us, R1 is the resistance of the primary winding, X1 is the reactance of the primary winding. So R1 X1 represents the resistance and leakage reactance of the primary winding of the actual transformer, right? Similarly on secondary side, let us R2 and X2 are the resistance and leakage reactance of the secondary winding of actual transformer. Okay. Similarly, to account for the no load current I0. What is no load current? I0. Of the actual transformer, I have drawn one shunt circuit in the primary circuit which consists of R0 and X0. R0 and X0. So this is your R0 and this is your X0. This is your X0. So your R0, why I have included R0 in this circuit? Because I will account for no load current I0 of actual transformer by putting the shunt circuit consisting of R0 and X0 in such a way that your E1 upon R0 equals to IC. What is IC? Core loss component of the transformer. Core loss component of the transformer. Right? Then second is nothing but E1 upon X0 equals to I magnetizing. This is the reactive current, so divided by X0. Where this IC and I magnetizing are the two quadrature components of the no load current I0 in the actual transformer. Now, what is the voltage given here? Voltage given to the primary winding is V1, right? So that current I1 will be circulated. This I1 has two components. Your I1 is equal to vector sum of IC and I magnetizing. Vector sum of IC and I magnetizing. And I2 dash. Right? So vector sum of these two is nothing but your I0. So I can write down I1 is nothing but vector sum of no load current of the transformer and load component of your primary current. Load component of the primary current I2 dash. So what is I2 dash? I2 dash is the load component of your primary current which is required to overcome the core losses which the primary has additionally supply. Okay, so this is about the equivalent circuit of the transformer. So we have developed the circuit which have the electrical characteristics similar to that of your actual transformer. Hence, this circuit is called as the equivalent circuit of the transformer. Here, this is your load. This is your load. Now, let us see how transformer will behave on load. How the practical transformer will behave on load. So, let us see that. So, just I will write down here transformer on load. So students, let the equivalent circuit which is I have drawn in the previous slide represents your actual transformer. Now, when your primary winding of the transformer is connected across AC supply of the voltage V1, So V1 is the voltage applied across the primary. V1 is the voltage applied primary winding of the transformer. Okay, so and suppose there is no load on the secondary, means your secondary is open circuited. So its primary will draw a small amount of current I0 from the supply, right? So I0 is your no load current. No load current. I0 is the no load current. This current has two components we have seen. What are those two components? IM. For I magnetizing, now onwards I will write down IM, and second one is IC. The magnetizing current will set up the mutual flux phi which is in time phase with the IM only. This flux which is in time phase with IM induces EMF E1 in the primary which is called as EMF of self-induction, and E2 in the secondary which is called as the EMF of the mutual induction. And other component is IC. Other component of I0 is the IC which is called as the core loss component. This component will provide the core losses, right? So now if the load is put on the transformer by connecting an impedance of finite value across the secondary winding. If the load is connected across secondary winding like I have shown here, if the load is connected, what will happen? A current I2 flows through the secondary winding and it will cause the voltage drop It will cause the voltage drop in the R2 and it will cause the voltage drop in X2 also. Hence, the secondary terminal voltage V2. What is the secondary terminal voltage? This one, V2. V2 is given nothing but equals to. Now, let us first of all, I have to mark here E2. This is the E2 is the EMF induced in the secondary on no load. Okay. So, when load is connected, current starts flowing through the secondary winding. Let that current is I2. This I2 will cause voltage drop in the resistance and leakage reactance of the secondary winding. So, this whole E2 will not be available across the load. So, I can write down V2 is the vector sum of E2 and the drops. So I will subtract the drops in the resistance and leakage reactance of the secondary from the E2 so that I will get the voltage across the secondary of the transformer. Okay, this is in volts. Okay, again I can write down V2 is nothing but E2 minus I2 Z2 volts. What is Z2? Z2 is nothing but the impedance of the secondary winding. Your Z2 is nothing but R2 plus J of X2 ohm. Okay. So, for I2 into R2 and X2 is nothing but your I2 Z2. The phase relationship between the secondary current I2 and secondary terminal voltage V2. The phase relationship between V2 and I2, this I2 is determined by the characteristics of this load. If my load is resistive, means my V2 and I2 both are in phase. If my load is inductive, means my I2 will lags V2 by some angle. If my load is capacitive, it means that my I2 will lead the voltage V2. I2 will lead the voltage V2. So, to neutralize now the magnetizing effect of your secondary current I2, means this I2 will produce, we have seen in last lecture, this I2 will produces the MMF N2 into I2, right? N2 into I2. So, to neutralize the demagnetizing effect of your secondary current, what my primary will do? Primary will draw some additional current I2 dash, in anti-phase with I2 such that this N2 I2 is equal to N1 into I2 dash. So, this MMF produced by secondary current get neutralized by N1 into I2 dash. So, what is my I2 dash? I2 dash is nothing but N2 upon N1 into I2, which is nothing but equals to K into I2. I have told this in last lecture also. Right? Thus, the primary current I1 on no load, this I1 current on load can be considered having two components. First one is your I0, which is flowing through the shunts, which is they are introduced in the circuit for considering to take into account the no load current I0 of your actual transformer. That's why I have included the shunt circuit consisting of R0 and I0. So, the primary current I1 on load can be considered as having two components, I2 dash and I0. So, students, I can write down my primary current is the vector sum of no load current and the load component of the primary current. Okay. So, vector sum of these two current is nothing but the total current drawn by the primary winding from the source. Okay, this primary current I1 causes voltage drops in the resistance R1 and leakage reactance X1 of the primary winding. So the primary impressed voltage V1 is therefore given by phasor addition of your E1, that is part of applied voltage which is balancing the E1, and drop I1 R1 and I1 X1. Again come to this. So what is this? This is nothing but your E1. This is nothing but your E1. EMF induced in the primary winding. So student, what is your V1? V1 is nothing but vector sum of E1 and the drop which is caused in the R1 and X1 of the primary winding due to the current taken by the primary winding from the supply. So mathematically I can write down my V1 is the vector sum of minus E1. Why minus E1? I will tell you, because I have to take the vector sum. That's why that E1 I have taken on the other side. E1 and drops in the resistance and leakage reactance of the primary winding. Right? Similar to this equation, I can write down V1 is the vector sum of E1 and the impedance drop in the primary winding. Okay, and the cosine of angle between your V1 and I1 gives the power factor on the primary side of the transformer. Will give the power factor of the primary side of the transformer. Now why this minus sign is taken? Let us consider this phasor diagram again. Yes. Now okay. So why I have taken that E1 minus? When I will cover the phasor diagram of the transformer on load, at that time I will tell you why that E1 is minus. For time being, remember that your primary impressed voltage V1 is therefore given by phasor addition of minus E1. Why minus E1? Because according to Lenz's law, that EMF is in such a direction that it will oppose the cause of producing it. What is the cause? Cause is nothing but the voltage applied across the primary winding. So this EMF, primary EMF, which is also called as self-induced EMF in the primary winding, will oppose the applied voltage, hence that EMF is taken as negative. But on the phasor diagram, how to take that EMF negative on the other side, or how to take it is negative, that I will tell you in the next lecture. So thank you students, thank you for keeping patience in the lecture. If you like this lecture, please don't forget to like, share and subscribe my YouTube channel. Thank you.